So I want to thank you all for coming. And I want to thank the organizers of the conference for inviting me. And I especially want to thank the organizers of the conference for putting me up right before the afternoon break. To that I say, challenge accepted. Okay, so today we'll talk a little bit about what I call the coming quantumpocalypse, and I hope it will give you guys some ideas about what you can do to take steps to protect yourself against it. So first off, let's give credit where credit is due. That title art, that cover art, is from a really bad, and you can see just how bad, 2010 TV movie called Quantumpocalypse, and I will not be discussing the movie today. Instead, I'm going to talk about where the intersection of quantum computing and cryptography, and hopefully how we can avoid ending up like that. Next, we'll be talking about these things. Memorize that. There'll be a test later. And let's start here. Why should you care about quantum computing? Because quantum computing can change your world. Here's our rosy future. Here's all the great things that our organizations are going to do. Here's all the things that we can dream and make happen, and it can turn to this in a heartbeat, in one day. But actually, that's really a picture of the Brooklyn I grew up in the 1970s. But no, that's no joke. And we call it the coming quantumpocalypse. It has the potential to literally be the end of the world as you know it. There is a technology that we'll talk about that everyone in this room and everyone you know uses every day, ubiquitously, probably thousands of times a day, and you don't even think about it. It underlines and provides the underpinning of the world we live in today, and that technology is under threat because of quantum computing. So the connected world that allows us to do what we do, anybody work at home, right? The connected world that lets us do what we do may go away in a day. So now that I have your attention, let's talk a little bit about that quantumpocalypse. And that quantumpocalypse is one possible future. There are many other futures. And we'll talk about how maybe we get to those better futures instead of the quantumpocalypse. So let's talk about quantum computing. What is quantum computing in a nutshell? Well, quantum computing is computing that doesn't work with transistors. It replaces transistors with atomic or subatomic particles. Right? We use atoms or electrons instead of transistors. Now, what's interesting about these atoms or electrons is that they can exist in more than one state at a given time. Can someone tell me what that attribute is called? Who said that? Okay, give that man a Cupid doll. That superposition allows operations to be done much more rapidly than with classical computers and with much less energy than with classical computers, which is good. Anyone familiar with Landauer's limit? Landauer's limit, look it up, is kind of terrifying because it posits the idea that at some point in the mid-21st century, we will have deployed and developed so many computing devices that the planet will not have the ability to supply electricity to run them all and anything else. However, quantum computing and quantum material science has the potential to make Landauer's limit non-applicable. So we like quantum for that reason. Classical computer, by the way, your smartphone, the laptops on your desk, they're all classical computers. Now, in those classical computers, a binary digit or a bit stores a single piece of information. And it stores it in one of two states and only one of two states. That's a 1 or a 0. Quantum computers use qubits, which are composed, again, of atoms or electrons. And they're kind of like bits because they can exist as a 0 or a 1, but they're kind of not at all like bits because they can exist as a superposition of both possible states, anything in between. So maybe it's a 1, maybe it's a 0, maybe it's some combination of both at the same time. It's kind of like DoorDash when it's there, but it's not there. It's Schrodinger's food. And this is kind of sort of what we're talking about. It's a useful visualization. So in classical computing, 3 bits can represent any one of these 8 different values. In quantum computing, 3 qubits can represent all 8 values at the same time. So the takeaways, right? Walk away with this. A qubit stores a whole lot more information than a conventional classical bit, and quantum computers can be really, really, really fast. So quantum, lots of speed, lots of computational efficiency. So let's segue over and talk about the real world and where cryptography meet. So everyone say hi, Alice. I can't hear you. I still can't hear you. Thank you. Okay, so there's Alice. Alice is a banker, major global bank, and every day she connects to servers and databases containing sensitive information, and sometimes they are all over the world. Now, this geographical distribution creates business problems for Alice. And the reason I do what I do is we use technology to solve business problems, because without the business problem to give a rationale for the technology is a neat toy, right? The difference between innovation and invention is noise, innovation solves problems, right? So Alice says, oh my gosh, how do I know that the information I'm receiving hasn't been intercepted? How do I know that the server I'm connecting to is the right server and not something spoofing it, making it up, and feeding me bad information? How do I know that I can trust the information I'm receiving from the server, that it hasn't been tampered with? Fortunately, since about 1978, 1974, if you're a Clifford Cox fan. Clifford Cox, anybody? Anybody? Okay, you all know Rivers, Shamir, and Edelman. You know Merkel. You know Diffie. You know Hellman, right? Okay, those guys got all the credit. Clifford Cox, because he worked for GCHQ, did all the work 4 years earlier and invented asymmetric crypto, but never got any of the credit. Anyway, because he couldn't. So, since 1978, that's the year the non-classified version came out, there's been a technical solution to Alice's problems called classical asymmetric cryptography. That's a lot of syllables, so I'm going to say asymmetric crypto. And it enables us to do a couple of things. We can securely share secrets to establish a confidential communications link. We can establish the identity of the party we're speaking to without ever having met them. We can ensure the integrity of the information we're sharing. And to create those benefits, asymmetric crypto relies on a type of math problem called a one-way function. What is a one-way function? Glad you asked. A one-way function is a function where we can calculate the output very easily. 2 + 2 = 4. Very fast, very easy, low bandwidth, low effort, right? But back calculating the inputs is really hard, to the point where it can't be done in polynomial time, where it's not computationally feasible. Is it 2 + 2? Is it 0 + 4? Is it 1 + 3? Is it 2.5 + 1.5? We don't know. We could spend a whole lot of time trying to figure that out. And a whole lot of time, in terms of asymmetric crypto, we're talking tens of thousands of years with classical computing devices. And I don't know about you guys, but I'm not really concerned that somebody's going to figure out my transaction with Amazon in 10,000 years. Call me crazy. So there are typical one-way functions that are used in asymmetric cryptography, such as integer factorization, elliptic curve, discrete logarithm, and you can see the types of crypto protocols that we use them in. This is now. This is today. But I want to take you back to the future. So, by the way, segue over, okay? I was told, no, we reviewed your slides. The fonts and everything look exactly the same they did on your computer. Yeah. Never trust the organized. Anyway, so let's go 5 years or so into the future, to be precise, and that's when the government is saying, hey, the cryptographically relevant quantum computers, also lots of syllables, CRQC, are going to be available. Now, for those of you of a more libertarian bent who tend to question things you hear from the public sector, let's talk about other people who said that, because it's not just the government. A little more than a week ago, Google and IBM engineers went on 60 Minutes and said, yeah, we're going to have it by the end of the decade. Guess which types of math problems quantum computing solves super fast? There you go. If those look familiar, they should. They're the ones that asymmetric crypto uses, and as a result, Quantum computing renders asymmetric crypto obsolete overnight. Boom. You know your remote keyless entry to your car? Asymmetric crypto. You know your credit card? Asymmetric crypto. Every web transaction you've ever done? Asymmetric crypto. I could go on, but you get the idea. It touches everything. And this means that post-quantum, we're not going to be able to establish identity, securely share secrets, or have confidential communications, or ensure the trustworthiness of our shared information. Remember that? Teotihuacan? Y'all know the acronym, right? If you take nothing else away from today, if you did not know Teotihuacan, take that away. It is a useful meeting word, okay? Right now, as we speak, literally, nation states and criminals are capturing copies of everything sent across the internet. There are data centers the size of cities outside of Beijing, outside of Moscow, outside of Dimona, outside of, not London, I used to know the name where GCHQ was located, outside of that, and oh, by the way, the entire state of Utah is one big flippin' data center. Guess who that belongs to? They're expecting in 5 years to own everyone's secrets. This is called the Harvest Now, Decrypt Later attack, and it's happening right now, and it means no more secure communications ever. The clock has started on the Harvest attacks. In fact, May 19th, Wall Street Journal, you can read all about the Chinese ship that's wandering around, plugging into undersea cables. What do you think they're doing that for? They are blatant about it. We're a little less blatant because we're a little more sophisticated, but we're doing it too. And that's why we call it the Quantumpocalypse. And I'm going to leave now so you can all be depressed for the rest. No, kidding. But I don't want you to panic, because there's good news. First off, the main symmetric crypto algorithm. Symmetric crypto, anyone? Y'all good on symmetric crypto? Gimme.
Instead of having a one-way function you use for data, you had a two-way function so that both sides are able to actually maintain.
That is an excellent geek response. Somebody give me the dumbed down response.
Shared secret.
Yes. OFK. One key. The F is silent, by the way. Okay? And that algorithm, AES, because you all use ACS and ECB, right? Everyone uses AES and ECB mode, right? Those of you nodding your heads, leave. Friends don't let friends use AES and ECB mode, okay? CNSA, the Commercial National Security Algorithm Suite, defined by NSA, AES is part of it. Wow, how can that be? Well, under a quantum attack, a 256-bit symmetric key would be as resistant as a 128-bit key is to classical computing attack today using something called Grover's algorithm. How secure is that? I'll give you an illustration. Let's say we have a supercomputer and it does 10.51 quadrillion operations a second. That's a lot of operations, right? Okay? And 1 year is about 31.5 million seconds. It would take a billion years to crack that 128-bit key with brute force. The second use of the word billion was not a typo. Oh, by the way, the universe is only 13.75 billion years old. So pretty secure, right? AES kind of rocks. In fact, it rocks so much that if you talk to cryptographers, symmetric crypto is not an interesting research area anymore because it's been solved. They go look at other cool stuff like random number generation and things like that. So yay, Cat's saying, yay, symmetric crypto, it's awesome, it's working. Also, for asymmetric crypto, there has been a tremendous investment in something called post-quantum cryptography, or PQC, lots of syllables. We love our syllables. So NIST has started publishing these PQC algorithms, such as MLChem, Module Lattice Key Encapsulation Module. Also, MLDSA. Supposedly, it was supposed to be the final version, the standardized version, was going to be out at the end of the summer. If you believe that, I've got a bridge to sell you, but it won't be much longer than that. NSA has said, here is CNSA 2.0. More on that in a little bit. Because NSA, for those of you who are in the tinfoil hat brigade, and I share, I much love, NSA is not inventing these algorithms. NSA is validating them for use in government and classified, okay? That's really important for commercial adoption. And commercial adoption is really important for support and vetting of the algorithms. It's a virtuous cycle. And the best news is PQC is now a matter of productization and adoption. It's not like the pandemic. It's not like, we got to start from scratch. That's not going on. We've got the algos. They've been looked at. They've been beaten up. They work. Okay? However, it's the implementations, as you all know, where the problems start to arise. Not all PQC implementations are equal. Thank you, Mr. Orwell. Most have to be taken with a boulder of salt. And here's why. Let's look at a typical notional crypto process. So crypto is not a discrete event. It's a chain of things, right? That's why we call them protocols. We use different pieces, different primitives strung together to achieve an outcome. So here's a typical one, right? Parties across the wire initiate a session. They say, great, let's initiate a session. Let's create some keys, some initial keys. Awesome, we have the tools to do that. We're going to establish our bulk encryption key. We're going to do some information exchange. We're going to monitor that session, and when it ages out, when we've sent a certain amount of information, we're going to blow away our old keys, create new keys, and this all happens automatically, and we rinse and repeat, right? Every time you log on to a website, right? Or every time you use IKEF2, right? All this stuff, normal. If any link in the chain, however, is broken, and the reason the chain is a really good analogy, is the chain fails, right? Bad guys say, hey, I don't want to work too hard, because bad guys have bosses and budgets too. Bad guys say, let's go after the weakest link. And what is the weakest link? Well, post-quantum, the weakest link is any part of the process that uses pre-quantum crypto, or classical crypto. And this is where concerns about something called hybrid PQC arise. By the way, if you ever hear the phrase hybrid PQC in meetings, I want you to all go, get away from me, Satan. Hybrid post-quantum crypto pairs PQC with classical crypto within the chain of the crypto protocol. And so this creates a weak link that's vulnerable to an attack by a quantum computer. And this begs the question, why? Why would someone do this? Well, I'm going to open up a can of worms for you. First of all, there's the ordering of things. Many of our current organizations, commercial organizations that are telling you they have a post-quantum solution, brought that solution out before standards were fully set. So they were early adopters. We'll talk more about the early adopter penalty in a little bit. Then there's the business logic. Technology costs money. Businesses like to have a return on their investment. Businesses, after they spend a lot of money and are told, hey, your stuff's broke. I was told I couldn't use the other words I wanted to use. Your stuff's broke. Look for reasons to say, no, it isn't. And there is actually pushback to public sector organizations saying, no, this is fine. No, this is fine. It's not fine. It's fine from the perspective of, we spent a lot of money on this. And then the standards are playing catch up. So NSA comes out with CNSA in September 2022, okay? All sorts of questions. And of course, with typical efficiency, they put out the clarifying guidance in April 2024. And among the things, and by the way, there was a big flippin' gap because the implication of CNSA 2.0 before the clarifying guidance was that hybrid might be okay. Well, the clarification specifically says, nope, you will be off classical crypto or non-CNSA 2.0 crypto, more on that in a little bit, by 2025, 2033, depending on what you're doing. And then there's the early adopter penalty. Early investors in a technology, any technology, I don't care if it's cruise missiles or cryptography, may not have the financial will or the ability, for that matter, to respend, to respond to real-world changes and advances in technology, even if that leads to really suboptimal outcomes. And I'll tell you a very quick story about that. the most prolific adopter of armored warfare in the world in the 20s and early 30s was the Kingdom of Italy. So they put out stuff like that. And it worked for the 20s and early 30s. It even kind of sort of worked during the Spanish Civil War. And then there was this little tiny technology enhancement event that we called World War II. And all of a sudden, they're no longer facing off against comparable technologies because the Americans and the Brits and the Germans have leapfrogged them, and the Soviets have leapfrogged them. And their armor can't keep up. They get whacked in the Western Desert. Why? Because they don't have the money in the budget to buy and design new tanks. This is a repeating cycle for all technologies for all time. By the way, Iron Hearts, Iron Hulls, great book on the Italian armored force. Okay, and then there's technical complexity. Swapping out a crypto protocol is hard, and it takes a lot of time and a lot of people saying, yea, verily. We took 10 years to go from TLS 1.2 to TLS 1.3. Hybrid solutions enable organizations to say, I'm doing something even while waiting for someone to do the right thing. So by the way, this is not a cryptography problem, okay? So if you find Daniel J. Bernstein in a bar, buy that man a drink, okay? This is a business problem because cryptography is everywhere, as I mentioned. It's built into your hardware, literally. It is in every piece of software, commercial software out there that moves or manages information, and if it's not, that's malpractice. The ability to do business, to create the commercial world which drives the GDP of every developed country is directly threatened by quantum computing. And so now you're saying, thanks, I'm going to go home and, basically find myself a farm somewhere, So the bad news first. There aren't many fully PQC products available today, so we can't spend our way out of the problem. Because this is the United States. If it doesn't work at first, spend more money on it until it works, and it'll eventually work. Two examples, the F4 Phantom and the M16 rifle. Extra good news, however, you can start doing stuff today to secure your development ecosystems against what's going on now, the harvest attack and the eventual quantum computing. So let me introduce you to CNSA 2.0, your new best friend. Okay? CNSA names 6 algorithms that are supposed to be quantum resistant for the next 3 to 4 decades. And first we have, for software and firmware signing, Leighton-McCallie signature and the extended Merkle signature scheme. Symmetric key. You'll notice there's only one bulk algorithm because it's the Highlander algorithm. There can be only one. No, kidding. It's the one that works. Okay? AES 256, again, friends don't let friends use AES 256 in ECB mode. We heart GCM. And for your hashing, SHA-2, but with 384 or 512-bit versions, which is interesting, by the way, because when this was being debated, we would have expected them to be using Ketchik or SHA-3, but which is supposed to be natively quantum resistant, but they went with SHA-2, so interesting stuff. And for the public key algorithms, the new stuff on new kids on the block are MLChem and MLDSA. They used to be called crystals Kyber and crystals dilithium, because cryptographers are kind of geeks, So things to do today, right now, RFN, right now the F is again silent. Ensure that your code at rest is protected with a useful variant of AES 256. And if you want to talk about useful variants, I'll be around for a little bit after this. Ensure that your hashing schemes focus on SHA-2, 384, 512, and start developing that organizational roadmap because you're going to need to convert. Within the next 6 months, adopt a post-quantum data in transit solution. Why? Because you people work at home. You work remotely. Everyone works remotely to some extent. Have laptop, will travel. Paladin, where do you roam? Nobody gets that. I'm going to go leave now. Anyway, okay. And what does that mean? post-quantum enterprise VPNs, post-quantum enterprise data center SDN solutions. They are emerging tech. They are out there. PQC managed file transfer and our data rooms, stuff like that. Because where is your stuff most vulnerable to the harvest attack? While it's in transit. Down the road, 18 months or so, well, we're sort of at the mercy of the industry and vendor adoption for this, but let's talk about what we're going to need to do to retool our internal IT to use PQC. Let's talk about policies, because nothing gets done without ridiculous amounts of paper backing it up. And let's talk about building those policies, not just for us, but for the constellation of organizations that we work with in order to produce value. Nobody produces value in and of themselves, right? It's all about information in, transformation, information out. So let's recap. Quantum computers are about 5 years away, but the threat they pose is happening now. This is like Y2K, but for reals. PQC can help mitigate that threat, but some PQC is not really PQC. So the only way to make sure that PQC is PQC is to get friendly with the standards and understand the standards, okay? CNSA 2.0 is a really good start. It's short. It's just a list of algorithms and a reason why for them. Ladies and gentlemen, thank you so much for your time and attention. It's been a pleasure.